jobs can we, thank you. All right, guys. Yeah, so let's get started for the day. So let's see, in terms of announcements and things, what, you're reading, is it reading week? It's reading week. Your reading assignments due this evening. Hopefully you guys have all read something. If you haven't, there's plenty of options on that list. None of them are terribly complicated. Well, that's not true. Actually, many of them are extremely complicated, but some of them are not. So if you need to do it at the last minute, I'm sure you can find something that's not too hard to read. Other than that, let's see, your next homework is due tomorrow. So I look forward to seeing more people, but not too many people in my office hours. So tomorrow morning seems to be the pattern. Although I wish there were more. I'm very lonely, you know. And then, let's see, next week is spring break, so it'll be pretty quiet, and then we're back on the usual cycle till the end of the course. Okay, so any questions for organizational things as usual at the beginning here? Fabulous. So, right, so today, like we tried to hint out at the beginning of our last class, we're going to embark upon sort of the next big chunk of 6838, which involves developing notions of calculus on curved objects. This is where I think those of you who did take an undergrad differential geometry course, it's likely to have dropped off, at least in my undergrad differential geometry class, beyond integrating a scalar function. I don't think we really thought about these kinds of things too much. But it turns out in the sort of modern version of this theory, things like operators and vector fields and all that good stuff really come to the forefront and are one of the primary means of understanding a shape, both in theory and in practice, right? And so in this class, we're going to try, as usual, to develop at least some intuition for the kind of things that go on in these areas. We're going to draw even more pictures than before because we're going to be relying on progressively heavier theorems that you would normally encounter in a graduate level geometry class, but the reality in our field is we need them, so we'll at least try to sketch them out, justify why the definitions make some sense, and in some cases sketch out how people think about proving these things, even if we don't have the formal machinery to do it carefully. Yeah? And so the way I've chosen to order this course is a little bit different from how like I know, let's see, it's kind of funny, this semester there's a class at MIT, a class at Carnegie Mellon, a class at Stanford that are kind of going through similar material, and I encourage you guys to look because they all have very different approach, and largely it reflects the bias of the different instructors involved. The way I've chosen to do it is to start with the Laplace operator first, because this is the one that we see in most of the applications, and then work backward to, in some sense, simpler operators that behave on vector fields. Right? Laplacian, you might remember from calculus class, is second derivative. So you might sort of ask, like, okay, well, what happened to the first derivative? And that's a totally reasonable question, and we'll come back to that when we talk about vector fields. In fact, our postdoc, Ed, wanted to give a course lecture, and so, of course, I handed off the one that I hate to give, which is the beginning vector field stuff. But we'll work together to make that a nice, clean thing. So anyway, that's the way we're going to choose to do it, is I think actually in exactly reverse order from at least the way Carnegie Mellon does, where I think they start with like D's and stars and things and work their way to Laplace operator. I mean, start with Laplace operator, build up a bunch of applications, and then go back and fill in that, like, oh, actually this thing is an example of an operator you can get from broader class of stuff. Okay? All right, so like we talked about last time, the other thing to be aware of is that there are many sign mistakes likely. In fact, just this morning I was going through my notes, I caught a few more. We also have reached the end of the written notes. I have been filling them in as we speak. Conveniently, next week is spring break. So I'm going to try and fill in a few more chapters during that week. And also what will happen for the remainder of this course is there will be lectures for which I'll send out a link to somebody else's notes, which are roughly instructor approved. So that's going to be our compromise here. Okay. All right. So we already talked about last time the basic motivation here, which dates back to it dates back earlier than this question, but sort of was really made famous by this mathematical article, which was asking, can you hear the shape of a drum? Right? I turn my head away from a drum. I hear the frequencies that it sends into the airwaves when I knock it, and then I want to know whether or not, given that list of frequencies, which at least in theory is infinite length, of course in practice probably isn't, but that's a separate matter, can I reconstruct this shape? Fun fact, by the way, if you have a finite list of frequencies, you can always construct a shape where that is the first k eigenvalues, and then the remainder of the spectrum is filled in some crazy way. This is a pretty modern result in geometry, and as you can imagine, it makes some pretty crazy drums. I don't think you could do this in practice. But in any event, what it means is kind of neat, right? It means you can engineer like all kinds of crazy instruments, and I guess at least if you have a lot of surface area to work with, you could make some pretty cool sounding stuff. We'll save that for the music department. So today, we're going to basically fill in this story that we sketched out last time, right? That I have a guitar, cello, violin, whatever. As I shorten the string, the pitch increases, and so there's some link between geometry, right, like the length of the string, and vibration, like the audio, the frequencies that I hear. Yeah? And so we'll explore this in 1D first, largely because it's easy. And then we'll expand to higher dimensional regions in Rn, and then we're going to kind of step sideways and talk about graph theory for a minute and see a similar theme shows up in that world. So in other words, like essentially my goal here is to show you that like there are a bunch of different roads that are all going to lead to the same operator. And then finally, time permitting, either today or next time, we'll define once and for all the Laplace operator on a submanifold of Rn. I realized this morning I didn't like the way that I defined it last time, so I redid the whole thing, and so now there's a lot of opportunity for a mistake, so get excited. Okay, right, so the basic area here is something called spectral geometry, and that's really just the key phrase for looking at the oscillation patterns, the vibration frequencies, and so on, and using those to tell you something about geometry. Okay, that's your sort of high-level vocabulary word for the day. Okay. So our goal here is to take this high-level phrase that we've used, right, this phrase vibration mode, and make it more precise, and we're going to do so on sort of a sequence of domains that are more and more complicated until finally we reach surfaces and I should say submanifolds. We won't do like Riemannian manifold here, although the reality is at that point actually the definition is basically the same. Okay, then we'll talk about discretization, all that good stuff. Okay, so right, so there are a couple things that we're going to need. I thought I'd remind you guys of a little bit of language before we go crazy here. The first is that we'll be talking a lot about operators in vector spaces. But now the vector space we're going to think about is the space of all functions on some piece of geometry. Right? So you can think of it like an assignment of a temperature to every point on a surface would be a function on a piece of geometry. Yep. And then essentially what we're going to do is work with operators that take functions and map them to other functions, right? So for instance, the differentiation is a totally reasonable example, right? I take a function considered as an object on an entire piece of geometry, right? Then the derivative, what does it do? It inputs a function and it outputs another function, which is the derivative. Yep. And differentiation is a great example of a linear operator, right? The derivative of a sum is the sum of the derivatives. And similarly, if I scale a function, then and I differentiate it, that's the same as differentiating it and then scaling. Yeah? And so there's a lot of commonalities between linear operators in these infinite dimensional spaces, like the set of functions, and just matrix vector calculus that we're used to from college class. Yep. And essentially, our goal today is to basically show that connection is quite deep, and exactly the intuition you hopefully have from linear algebra class. If you don't, this will be a great time to fill in a little bit of that. It's going to apply to this crazy infinite dimensional case without a whole lot of change. Okay. Of course, there's some terminology here, and as you might remember from our second class, what we used to call matrix vector products. In this class, we're going to think of as linear operators, right? So the linear operator corresponding to a matrix vector product is the operator which inputs x and outputs a times x. Yeah, so you can think of it like a piece of code, right? The piece of code takes in a vector and outputs another vector, right? And what you might recall from our second lecture was we showed that if our piece of code is some black box, but it satisfies those two axioms of linearity, then if x is finite dimensional, secretly that piece of code is matrix vector multiply. Yeah? In other words, there's always a matrix hiding behind any finite dimensional linear transformation. Yep. And that's the thing that I think we all kind of knew, but you maybe hadn't proven explicitly, so it's always good to go back and double check. Okay, so we're going to need one additional thing from linear algebra class. I keep saying this, like, well, just one more thing that you're going to need from calculus linear algebra class that you probably remember and didn't like a whole lot if you're in computer science department, and that is this spectral theorem. I just remember spectral theorem. About half and half. That's okay. So remember, essentially, symmetric matrices have a lot of nice properties that asymmetric matrices don't, right? In particular, what the spectral theorem tells you, by the way, the C here for complex numbers is sort of unnecessary. If you prefer real numbers, that's fine for today. What the spectral theorem tells me is if I have a symmetric matrix, or in Cn, a self-adjoint, Hermitian matrix, whatever, then necessarily the eigenvectors of that matrix span Rn, meaning that I can come up with a basis for the space that the matrix acts on, and that basis includes the entire space, and that basis is orthonormal. Right? And so that's this magic that basically symmetric matrices give you, is that if you have a symmetric positive definite matrix, you get an orthonormal basis, and all the corresponding eigenvalues are non-negative. Yes? Did I already make a mistake? What was that?
Positive eigenvalues, right?
Oh, I suppose, yeah. Positive definite means positive eigenvalues. Positive semi-definite means you can have a zero eigenvalue. Yeah. We're going to see actually the Laplace operator is semi-definite because it has constant functions in null space. In fact, there's some modern topological literature that says, like, well, let's say I have a piece of geometry and I want to know how many connected components it has. So there's a very easy algorithm you could do to figure this out, right? It's just flood fill, right? Like just take a point, flood fill. If there's points left, choose another one, flood fill again, and keep doing that. And that's the number of connected components. If you wanted to be really fancy about it, you would take the Laplace operator, compute the null space, and the dimensionality of that is exactly the number of connected components. Because that's like the dimensionality of the set of constant functions, which is not necessarily zero, right? If I have two objects that don't touch each other, I can put a constant thing here, a constant thing here, and somehow those two things can be linearly combined and still a constant, even though the value is different on the two pieces. Yeah, and so right, and that thing is actually suggestive of sort of higher order topological constructions we'll see for like detecting donut holes in future lectures. Right, so this is the other object we're going to need. Just if you've forgotten from linear algebra class, you have a symmetric matrix, then you have a full set of eigenvectors. If you have a positive semi-definite matrix, then you have eigenvalues that are non-negative. Yeah, that's the basic language here. And this plays out in code, by the way. This isn't just abstract, right? Like there's plenty of numerical linear algebra code out there that takes the symmetric matrix and gives you the eigenstuff back. And indeed, we're going to use it in your, probably your next homework, 2 homeworks from now? Next homework. Yeah, next homework. Okay. Right, so here's our progression. We're going to do line segments, then regions in Rn, then graphs, then submanifolds. Notice the only one of these with curvature, well, the only one of these with curvature we've defined so far is the last guy. And that's going to make things a little tricky. Okay. So to start out, of course, we've been talking about vibration modes. We should probably like double check that the Laplace operator has anything to do with vibration. Seems like a good start. So let's draw a picture of the physical system that we have in mind, at least for one dimension. And we're going to take a really lame limit to get to the wave equation that we all know and love. And I'm sure the physicists in the room will cringe at what's about to happen because I am uncomfortable with it. I don't like physics. Okay, so let's say that I have a system here, and there's n+1 particles. And they all sit at a bunch of integer points, or not at a bunch of integer points, rather at a bunch of evenly spaced points at, let's go with x. This is x equals 0. This is x equals 1. Okay? Just a bunch of particles. They all have mass m, in case you were wondering. And furthermore, I connect each one of the particles a little spring. Yep. This is our favorite one-dimensional vibration-looking kind of thing. Yeah. So what I'm going to do is I'm going to come up with a variable, which is u. So we have u0, u1, u2, and so on. And these variables, by the way, we'll call this distance h. These variables are all just the sort of displacement of this particle from the rest position, which is just evenly spaced. Cool? Okay, so let's say that I have a bunch of springs, and the spring rest length is 0. So the spring wants to just be as tight as possible. Then this equilibrium here is only by virtue of having attached to these two endpoints. Yeah? So since it's all a bunch of copies of the same spring, these points, if the system were resting, would be all evenly spaced. You can see your instructor really doesn't like doing physics. I'm already like confused and upset here. Okay, so right, so let's take a look at the forces on a particular particle, right? There's one here, there's one here, yeah? I forget, did I call the U's positions or displacements in my course notes? Let me double check. Yeah, we'll say it's a sign distance from the rest position here. Okay, so in that case, what is the total force on particle I here? Well, there's sort of two different sources, right? One is the spring pointing this way, one's the spring pointing that way, assuming I'm not at the endpoint. Yeah. So in particular, if you work it out, what you'll see is that you get, right? This is the force involving the guy on the right-hand side, scaled by the spring constant, right? And similarly, on the left-hand side, I get another force. I always get the signs of these backward, which is why I keep shaking my notes, right? Because the forces point opposite ways. Yeah, and of course this is equal to what? Well, it's equal to the mass of the particle times the second derivative in time. Yeah, and this is what's governing the dynamics of these wiggling little particles in a big line of spring. So like I can take one of these particles, pull it a little bit horizontally and let it go, and then all these things will vibrate around. Yeah. By the way, notice in this picture, I'm drawing a transverse wave. The wave is propagating horizontally. The typical picture people draw for these things is to pluck the string, like a violin or something. This actually makes me a little uncomfortable because there's an angle that you plucked at, and there's a Taylor series that happens when you derive the wave equation that way. And I don't buy it, but we'll come back to that another time. Like we solved the wave equation for large t, but somehow we're happy to use a Taylor series at t equals 0, and to me that's a little strange. But the transverse option is perfectly fine. Yeah. So I pull this thing a little bit. I have a slinky. I pull it, and it starts vibrating. Yep. Okay. Great. So let's simplify this expression. Of course, this is k times ui plus 1 plus ui minus 1 minus 2 times ui. Yep. This is just algebra. Okay. So let's think for a second. How do I approximate second derivatives of functions? Well, you're using this expression. Thank you. Yeah, probably divided by h somewhere. Yeah, but roughly, well, what is the first derivative? Well, it's like the difference here, right? That's like some kind of first derivative. And what did I do here? Well, I kind of subtracted those two differences, so I got like the derivative of the first derivative. Yeah. And that's exactly what gave me that 1 minus 2, 1 kind of stencil that happened. Yep. So this is where the sleight of hand always happens in a PDE textbook, is to say, okay, so if I think of u kind of like a function on a line, right, giving the displacement of every particle, yeah, then roughly, if I squint at this thing and I just start increasing the number of particles along the line, right, then the dynamics of this thing in the limit starts to look like a partial differential equation, right, which I can write. This arrow hides a lot, right, because we're like taking a limit here, and I haven't even defined what it means to take a limit. But I think this is a pretty typical arrow to draw. We're going to have the following. Right, so this is the second derivative in space. This is the second derivative in time. And the c is hiding all the constants I don't want to deal with. So this includes the spring constant, the mass of the particle, h, whatever you need to make the limit work out. Okay? Obviously extremely sloppy math. But the point here is that this PDE is totally natural, and it really does come from physics, right? It's just saying that it's talking about things that are propagating along a big line of springs. Yep. And so let's step back and make sure that we understand what this thing is saying. So first of all, u is a function of x and t. Right? So in other words, this is the displacement of every particle, right? So sort of the starting point of the particle is x here, and then the t here is time. So that's this is a partial differential equation because it's coupling those two things together. And why does it make sense that it's a second derivative? Well, so what does a second derivative measure? It measures kind of concavity, right? So somehow if a particle is displaced weirdly relative to its neighbors, then it wants to go the other direction. Right? And that's all this PDE is saying. So it's a pretty natural object. And this equation here is something that we call the wave equation. And of course, if you take a physics class, this is an extremely important object you spend a lot of time analyzing. Okay, so everybody cool so far? Nothing too exciting. Excellent. All right, so now let's start putting a slight spin on this story. Essentially, we're going to tell the same story 5 different times, just in like more general language each time. And let's go back to this one-dimensional but finite example here, and think about a different way of notating the same problem. In particular, I'm going to define a particular matrix, which I'm going to call L. We're foreshadowing. And L is going to look like the following. It's going to be 2 minus 1. Already forgot. Oh, no, minus 1, 2, minus 1, minus 1, 2, minus 1, and so on. And then we're going to get a minus 1 and a 2. It's a banded matrix, right? Band whose width is 3, right? Then a different way to write exactly the same dynamical system, but just stack all of the u's together and have them all evolve at once, would be to think of u as a vector of all of the displacements. And then what do I get? Well, I get that u double prime is equal to minus LU. We're here, I'm going to ignore this. I'm going to assume the spring constant is 1. I think that's, hopefully we're all okay that the spring constant doesn't really affect the qualitative behavior all that much. Cool? So look what happened. There's a matrix hiding inside of here. Yeah, and essentially that matrix is the thing that's going to tell us quite a bit about the geometry of our system. First of all, I've noticed, by the way, I've chosen a particular sign for L. The reason I've chosen it this way, a good homework problem for you guys, is to go back and double check that this matrix is positive semi-definite. In fact, I think the way I've written it here is positive definite. And of course it's symmetric. Yeah. Okay. Everybody with me so far? Nothing too exciting. Fabulous. So, right. So what does this mean? Well, let's say that I wanted to solve this ODE. In fact, I can forget where the ODE came from. I just have a linear second order ODE. Anybody know how we go about this? We use the spectral theorem. Yeah. So in particular, let's assume that L has a bunch of eigenvectors, right? And the eigenvectors are phi k. These are in R to the n, I guess, plus 1, the way I've notated it here. Right. And then, actually, the way I'm going to notate it here, maybe we cut off the beginning and end, so it would be n minus 1. Just for fun. Whatever. Okay, so great. So one thing that I can do is say, actually, I can always take u of t, and I can write it as a big sum, right? I can write it as uk of t phi k, right? And this is just expanding something in a basis. I haven't done anything too exciting here. Right? And the reason we can do this is by the spectral theorem, right? The spectral theorem tells us that this basis is full and spans Rn. Yep. N minus 1. Well, I'm going to get plus and minus 1s off a lot today. Okay. Fabulous. So if this is the case, well, then what can I do? I can say, by the way, there's a slight typo in the notes I'm noticing now, but that's okay. So what is u double prime? Well, it's nothing more than the sum uk phi k. Yeah, so that's one side of the ODE. And what's the other side? Well, okay, so minus LU is equal to times minus L phi k, yeah, just by distributive property. But look, how did I choose phi k? Well, it was an eigenvector of L. Yeah. So this is of course the same as minus lambda k phi k. Right? And okay, so what have I done here? So I've in effect said this expression is equal to that one. Do you see that? Assuming the wave equation. So I'm in a basis. My basis is orthonormal, in fact. So what does that mean? And it means that, in effect, every coefficient is equal to every other coefficient. sorry, I phrased that poorly. Every coefficient here is equal to every coefficient there, right? Because the phi k's are the same phi k's. Yeah? So in other words, what I have is now a one-dimensional ODE problem, right? I have 2 minus u. There. Right, and the way that I did that, I started with a vector ODE, I wrote it a basis. I wrote two different expressions on the same basis, so in effect, the coefficients have to equal one another. And that's all. Did I make a mistake? Yep. Sorry. Absolutely right. Okay. Anybody know what the solution of this thing? Remember that by construction, the lambda k's are greater than or equal to 0, by the way. These are positive numbers. Yep. Well, let me give you an example. What's the second derivative of sine? Minus sine, right? Because the first derivative is minus cosine. Second derivative, nope, got that wrong. First derivative is cosine. Second derivative is minus sine. Yeah? So in some sense, it satisfies this ODE with lambda equal 1. Yeah, so the slightly more generic thing to say, and if you haven't taken an ODE class, I'll let you fill this in at home, is that we can write sine, I always get these coefficients wrong. This is just a fact from one-dimensional differential equations class, right? So in general, if you have, x prime prime equals minus x, right, then that's the equation of an oscillator. Yeah, and so what you get is this solution here, which kind of makes sense, right? I mean, we're used to talking about the wave equation. Cosine and sine are good bases for waves. I haven't given you boundary conditions, so it's kind of reasonable to have both of them hiding here. Yeah? For some generic coefficients that we haven't defined. Okay, so when we talk about frequencies, finally we have them, right? Because essentially they're hiding right there. Yeah? So the square roots of the lambdas give us our vibrational frequencies, and that's what we're looking for. Okay. Everybody with me so far? I think this is a kind of a familiar story from ODE class, which is good because I'm bad at physics and will undoubtedly get it wrong. Okay, so now the question, and the thing that matters when we're doing geometry, of course, is we're not in the discrete part of our lecture yet, is can we parallel that story? And I would say yes. So in effect, what is L? L is a linear operator, and it takes some discretization of a function on a line, and it maps it to minus its second derivative. Yeah? So now I'm just going to define a new operator, squiggly L, which now operates on smooth functions rather than functions with one number per point on this line graph. And what it's going to do is going to take a function, not that, a function u of x. For this purpose, the spatial variable doesn't, or the time variable doesn't matter yet. And it's just going to map it to another function, which is minus the second derivative. Yeah? So L is a thing that takes in a function and gives you back another function. That makes sense? So let's check a few fun things about L. So remember a couple lectures ago we defined kind of a dot product-like thing for functions, right? So if I have two different functions, u and v, I can define their inner product. Yeah? And remember what the definition of positive definite matrix is? Yeah, it would be like U transpose L U is greater than or equal to 0. Right? That's what positive definite means. So let's take a look. So we now have, so remember that U transpose times a vector is like a dot product. We have some notion of dot product. We have some notion of matrix vector product. How do you think we're going to prove some kind of inequality like this? I suppose you could. Yeah, we only have like sort of two tricks in this class. But we're going to use the other one, which is integration by parts. Yep. So in particular, let's assume for a minute that u, by the way, we'll go from 0 to 1 here. Let's assume that u of 0 equals v of 0, u of 1. So in other words, our spring is kind of held at the ends. Yeah? Okay. Then one thing we can check is essentially just a notational trick. So let's say that I have a function u. I can look at this inner product, right? So this is like u dot product with L applied to u. Take a look. So it's just like this expression here. But now let's unpack it a little bit, right? So this is the integral from 0 to 1 of u of x times minus u double prime of, it's an x, dx. Yeah? I've been lazy, and I've made my everything possible at the endpoint 0. Yeah? So what happens when I integrate by parts? Maybe I do this too, just for fun. Whatever I need to be 0 on the endpoints, I'm going to. Essentially, that's not the important part. Okay. Well, so that's some boundary term, which we can safely ignore, minus, so I'm going to cancel this thing. Squared. Right, because I take one of those primes and I move it to the other guy. Okay, so that's an integral of a number squared. That's greater than or equal to 0. Yeah? Okay, so now we're seeing that our connection here is getting deeper, right? I have some operator that shows up in my smooth wave equation, and that operator is some version of positive semi-definite. Yeah? And in fact, there's a generalization of the spectral theorem to any Hilbert space with a certain structure and nice bounded operators, right? Conveniently also called the spectral theorem, which tells you that actually this object admits a basis as well, assuming fixed boundary conditions. And those are exactly cosines and sines, right? Because those are sort of the eigenfunctions of this thing. And the additional fact that we're not going to prove is that those things span the space of functions, but we already kind of knew that if you took Fourier analysis class. Right? It's exactly the same basis, right? So in fact, what are the eigenfunctions of this thing? So generically speaking, let's say that my interval has length L, and that I have fixed boundary conditions, meaning that I held the endpoints of my wave fixed, and I just allow it to vibrate at the inside. Right, then essentially what do I have to do? I have to engineer sine waves that like kind of run into the two endpoints and have an integer number of wiggles. Yeah, and you can double check that that basis is exactly I always get this stuff a little wrong. Yeah, so you can check that phi k of 0 and phi k of L both equal 0, right? Because this guy and L kind of cancel out, and I'm left with pi times x. Yeah, or pi times 1, k 1. Right, and yeah, and this is the thing that makes this square integrate to 1. So this is kind of optional, but really the thing inside is what matters. Yeah? So we've sort of come up with exactly a parallel story. Right over here, we came up with a symmetric positive definite matrix, so we had a full basis, and that allowed us to solve the wave equation in closed form. And it turns out we can do exactly the same thing here, where we come up with a symmetric positive definite operator now, semi-definite operator. Its eigenfunctions are here, and indeed, you can follow from there, you can follow exactly the same formula to solve the wave equation in smooth case. Yeah? So, why do we go to all this work? Well, for one thing, what are the eigenvalues corresponding to this thing? It's quite simple. Remember, I differentiate twice, so I get 2 of these factors that come out. Yeah, so the kth eigenvector here is equal to pi k over L squared. Of course, there's an infinite sequence. Notice that they grow quadratically. That's going to come back later. Okay, so here's my question. Can you hear the shape of a line? Line segment, rather. Yes. Do you see that? Because hiding in this expression for lambda k is an L. In fact, you don't even need the full spectrum. Yeah? If you just give me the first eigenvalue, you can already hear the shape of a line. First non-zero eigenvalue. Yeah? So indeed, in one dimension, the can you hear the shape of a drum question you can answer positively. Namely, if I give you the sequence of Laplacian eigenvalues associated to that piece of geometry, I can read off from that sequence everything I need to reconstruct the geometry of the shape. Yeah? This is like not a particularly profound observation in one dimension, but I don't think that we typically think about this computation this way, which is just this one additional step, which is that hiding inside of this sequence is what? Something completely deterministic that I can get rid of, and one thing that maybe I didn't know about my geometry, which is the length. And in one dimension, that's the only geometry you have, so you're done. That makes sense, the story here? Fabulous. So that's it for the one-dimensional version of this thing. But notice that, like, despite this probably being something you might have seen before, in some sense, you've seen Fourier analysis, you've seen eigenvectors of matrices and using those to solve an ODE. The one additional thing is just to notice that the eigenvalues here encode something about length specifically, and that's what's relevant for our class today. Yep. Incidentally, anybody know what the eigenfunctions or eigenvectors of L are? Any ideas? L is a circulant matrix? It would be. What's that? Oh, fine, because of my boundary condition. Yeah, fine. I could, if I had a bunch of springs linked together into a circle, I could put a -1 on the left-hand side in the last row, for example. Then what would the eigenfunctions be? It's exactly a discrete Fourier transform. The whole thing fits together. Yeah. Okay. Right. So that's the basic picture that we've drawn here. Is that if we look at, rather than thinking about Rn, our favorite vector space, we're going to have a new vector space which is smooth functions on the interval from 0 to L. I can define the Laplace operator as the thing that takes a function and maps to minus the second derivative. Again, that minus is the thing you should be suspicious of because I'm going to get it wrong later. Just get excited. Right? This L is somehow a positive definite matrix, and indeed, it admits a bunch of eigenfunctions, and the corresponding eigenvalues tell you all the geometry information you need to know. Yeah, that's the basic picture in 1D. Not so bad. Okay, so, right, and of course the intuition you can have if you like this can you hear the shape of a drum thing is that really the operators that we looked at, by the way, we added some boundary conditions, namely that nothing interesting happens at the endpoints. That's going to be easier for us later when we talk about closed surfaces because there won't be a boundary. But for now you should be more careful about this than your sloppy instructor typically is. Okay. Excellent. So yeah, so far our answer is yes. Can you hear the shape of an interval? And indeed, the one-dimensional Laplacian does tell you lots of geometric information. So one kind of fun one is if you take the gradient of arc length, one thing you can basically read off of your first homework is that the Laplacian applied to the coordinate function. So you think of the map from points on this line to their positions in 2D, really does give you that gradient of arc length. And when we talk about mean curvature flow, we'll see this is one way to implement it. Yeah, so it works in lower dimensions also. Cool, so that's part one. We've talked about line segments. So now let's lift just one dimension to regions in Rn. And really this story isn't much different. You can see I'm bad enough at physics, I'm not going to attempt to motivate the wave equation in 2D because I think I'll just get it wrong. But rather, I refer you to any number of physics textbooks out there. But the basic picture here is one that you guys have probably seen before, right? So Laplace operator now takes functions on some domain. By the way, n equals 2 is perfectly fine here. The n isn't going to matter a whole lot for our discussion. Yeah, so in general, this is the notation I'm going to try to stick to in this class, which is omega refers to a flat region. There's no curvature here. Okay, and then this little partial sign here is the boundary. So this is a curve that goes around the outside. I think this is stuff we've seen before. Well, so then I can talk about the space of all functions on omega, right? So this would include something like u, right? And the wave equation is that the second derivative of u in time is minus Laplacian of u, where Laplacian is now the sum of all of the second derivatives in all the different coordinate directions. Okay. By the way, notice that there's something like a little non-physical about the way I've written this equation. I think this is the typical way you see it in physics class. Should like physics depend on the rotation of my drum? No, right? Like if I rotate my drum by 30 degrees, I expect the vibration to rotate by 30 degrees. It's not actually totally obvious from this expression here. Do you see that? Because it's summed up in coordinates, and that's actually a thing that you really should, check that like physics doesn't depend on your choice of axis. Of course it doesn't, and you can go back and just double check that the physical system just tells you this is the right expression. But it already kind of tells you from a geometric perspective, this is a bit of a weird way to write this operator. Yeah? Okay. Right, so there are many different ways to notate and describe this operator, which I'm going to talk about while I tie my shoe. And let's see, let's go to the next slide here. So a very typical piece of notation, which in Rn makes a lot of sense, but we're going to see leads to some kind of misleading math in the curved case, is to think of Laplacian as div of grad. How many of you guys have seen this notation before? Yeah, so notice that like the dot there really is some kind of dot product, right? Where I'm thinking of this thing, right? This thing is an operator, but I can think of it like a vector that contains a bunch of operators that take the partial derivative in different directions, right? And so this dot product is secretly the sum of like d over dx1 squared. So it's like the second derivative in the first guy, second derivative in the second, and so on, right? So this is just a notational trick. Again, right, so what are the main things to notice here? That one way to get to defining a Laplace operator is instead to define divergence and gradient and put those two together. Yep. We sort of already have some notion of gradient on a surface, right? We have this exterior derivative, this d operator we've used a few times. Do we have a notion of divergence? Not really. We can't really take the transpose of what we have. That doesn't make any sense. Yeah? So anyway, it's just kind of a funny thing. Actually, if you look in many geometry processing course slides, you'll see this expression as the definition of a Laplace operator on a surface. I think this is extremely sloppy, so we're not going to do that here. Okay. Of course, there are many things you should check. Probably the simplest one is just that if I rotate my shape and I apply the Laplace operator, that's the same thing as applying the Laplace operator and rotating it, which we know from physics, but actually is not totally clear given the expression. In fact, maybe it's a good homework problem to just double check. Right. So since I don't like physics, I thought instead we could motivate this in a completely different fashion just to see yet another place where Laplace operators pop up. And this one I think is more familiar in the machine learning world. So let's say that I have some function which is unknown in this domain, and for whatever reason I do know it along the boundary. This sounds a little ridiculous, but it's not terribly crazy, right? I mean, oftentimes I'll have a data set, it's kind of sparsely sampled, and I want to interpolate it to the rest of my domain. Yeah? Well, sort of in the absence of any additional information, how might I do it? Well, one thing to say is like, in between the points where I know values of my function, it might as well be smooth. Yeah? Like I might as well kind of smoothly interpolate from one value to the other. For example, if there were like a local maximum of my function here, and the only data I had was on the boundary of this kind of chess piece thing, that would be somehow a very suspicious interpolant, right? Because there's like an interesting feature here, but it's at a point that like we don't know anything about. Yeah? So one thing I might do is sort of take the variational approach here. Again, we only have like 2 tricks in this class. We've already used integration by parts, so we should use the other one. And that looks something like this. So one thing that I think is very familiar in machine learning world is say, okay, I don't know the object I want, but I can measure a lot of things about it. Yeah, and one thing I can measure is kind of how smooth or crazy my function is, right? Like somehow this thing would be an undesirable interpolate of my boundary data. This thing probably more so, just in the absence of other information. Well, what distinguishes these two objects? Well, this one is wiggling around a lot. And so what does this gradient look like? Well, the gradient is somehow quite crazy, right? Because the gradient, remember the gradient is the direction of change, and apparently there's a lot of it. The function keeps changing. So if I wanted to measure that directly, what could I do? I could take the gradient of my interpolant, which is unknown, but I just want to measure how smooth it is. I could take the gradient and just take its norm and integrate it over this whole thing. And well, when is that number small? Well, it's small probably for the function on the right and large for the function on the left. Does that make sense? So this measurement, this number is shown at the top of the slide here. This thing is called the Durational Energy. I don't know. And essentially, it inputs a function u and outputs a scalar. This is going to sound kind of familiar to your first homework. And that scalar is exactly just the total norm of the gradient of u integrated over the whole domain. Notice if I want to do this carefully, I have to talk about function spaces, all that good stuff. But in this class, we're not going to worry about it. Okay, so what do I have so far? I have like this kind of little probe, like a temperature probe kind of thing, right? I can input a function and this thing tells me how crazy that function is. And probably what I'd like to do is solve my interpolation problem by just minimizing this energy subject to the constraint that it matches the known values. Yeah, so now it's starting to sound like a statistics problem. Okay, yeah, so let's do that. So let's say that I want to minimize this energy everywhere where I don't have information. So how are we going to do that? Well, let's say that I have a function u, and remember the u on the boundary is kind of prescribed. Yeah? Yeah, I'll do it the way I did in the notes. Okay, so here's my energy E of u, and remember by definition it's 1/2 the integral over omega of mod, like that, I guess dA if you like. And of course I can just write this slightly differently, right? This is dot product with grad u a second time. And what is this screaming out to do? Integration by parts, yeah? So in particular, okay, so let's say that I integrate by parts. What's going to happen? Well, in this case, I really can't ignore the boundary because I have boundary data. Yeah. So what am I going to get? Well, my boundary term, yeah, is going to be. Remember what happens? I'm going to be popping one of the derivatives off and moving it here. So it's going to look like u dot product with the normal to the boundary. D. By the way, this notation is suggestive, right? There's area and there's length. Really, it's just one dimension lower here than here is what really matters. But 2D is fine. Like, really, you don't have to worry about it. Minus the integral over omega of what? Well, there's still 1/2 there. And now I move the gradient here. Well, what's that? That's div of grad. So that's exactly Laplacian. Yeah? So this is u. Oh, so I snuck that a plus sign because I defined Laplacian to be minus div of grad. Cool? Okay. So far, I haven't told you how to minimize this energy. I've just written a different expression. Yeah? So let's think from a variational calculus perspective for a minute, our favorite tool here. Right, so let's say that u locally minimize this energy. Yeah? What would that mean? That would mean if I perturbed u a little bit, the energy would get bigger no matter how I perturbed it. So in particular, if I kind of take that one-dimensional slice through my perturbation, the derivative as I move in that slice direction has to be 0. Right? That's the reasoning we keep applying here. First of all, we have fixed boundary condition. Right? So u must satisfy the prescribed values along the outside. So what do we know about, let's take a perturbation. And let's call him W. Right? What do we know about W? Well, in order for it to be kind of a valid perturbation, in other words, to say that I have a local minimum subject to the boundary condition, what do I know about W on the boundary of the domain? Is 0, right? Because that's the only way to preserve the boundary condition as I perturb, right? So I can write W restricted to the boundary is 0. Okay? Sneaky, huh? Okay. So now, what do I know? I know that 0 is equal to d over dh, our favorite expression of E of u plus hw evaluated. That's that thing. Oh boy. W evaluated at h equals 0. Whew. Yeah. Okay. So let's write this expression really quickly. Well, we have. What do we have? Well, on the boundary, notice what's going to happen is I'm going to get a bunch of terms involving W that are all going to go away. So I'm going to have a boundary integral of something that only involves U, dl, right, just by my boundary conditions, plus this expression here, and this is where I have to be a little more careful. right? So this is 1/2 integral on omega. And now what am I going to have? I'm going to have u Laplacian u plus 2h, nope, that's a lie, plus h u Laplacian w plus h w Laplacian u plus h squared w Laplace w. Right, I think those are all the different cross terms. Okay, great. So what happens if I take d over dh of this expression and then set h equal to 0? Well, when I take d over dh, this term vanishes, and this term vanishes. Yeah? Because there's no h there. There's a 2h factor that's going to show up here. Right? So that's going to vanish because I take h equal to 0. And I'm left with is just these two cross terms. Yeah? So in effect, what do I get? I get that 0 is equal to 1/2 the integral over omega of u Laplace w plus w, like that. Did I do that right? Yeah. Okay. So I'm almost where I wanted to be. But unfortunately, there's this term here, right? There's a derivative sitting in front of my perturbations, not so great. How am I going to get rid of it? Integrate by parts. That's right, because it's the only thing we know how to do. I want the derivative in front of u. I have it in front of w. Yeah? So I integrate by parts 2 more times. And what am I left with? I'm left with just a second copy of this term here. Yeah? W Laplace u. Okay? Everything cool so far? Oh, in case I have to be sloppy, I can assume that w is 0 in like a neighborhood of the boundary or something. Like anything I need to make it, to ignore boundary terms is okay here, because really I'm just concerned with the inside. Yeah? Okay, so this is true for all w that don't touch the boundary. Any choice of w. Doesn't matter what, I get 0 when I take this integral against w. So using the same logic that we've applied a bunch of times in this class, for our final trick, we know that the Laplacian of u is identically equal to 0 in the interior of the domain. That's extremely ugly handwriting, I'm sorry. Okay? So this is once again just an application of the same type of calculation we keep doing in this class, right? We have our favorite objective function. We say, like, suppose this is a minimizer. Now take a slice through something that would edit it. Then it's going to get worse. So if I take the derivative, I get 0. Integrate by parts a bunch of times, and I get some expression. It's the same you did on your homework. It's the same we did when we took variation of arc length. All that good stuff. Yeah? Okay, but what did it tell us in this case? It told us that if you minimize Dirichlet energy subject to these conditions, conveniently they're called Dirichlet conditions, yeah, then away from the boundary, the Laplacian of u is identically equal to 0. Functions that have this property, right, Laplace of u equals 0, have a special name. These are called harmonic functions. Yeah? Notice the word harmonic, yeah? I mean, there's a lot of audio terms that show up in this area of math. Yeah? And harmonic functions have a huge amount of nice properties to them, enough to fill many classes in the math department. In fact, I believe they do. You know, depending whether you take complex analysis, harmonic analysis, PDE. Most of these are just analysis of harmonic things. I thought I'd just draw you some fun pictures of a few nice properties. For one, these functions can't have local maxima in the inside. That somehow makes sense, right? Because if you had a local maximum, you could kind of cut it out and replace it with something smoother. There's like never a reason you would need one of those. A slightly more refined version of that is something called the mean value property. How many of you have seen this in some context or another? Interestingly, not the same group. So the mean value property is this really funny kind of corollary, again, of integration by parts, roughly, which is if I draw like a little disk in the inside of a harmonic function, and I average the value of u, then it equals the value right at the center, which is pretty crazy if you think about it. And these are very hard functions to just cook up without solving PDE. Okay, but that's not our point here. Of course, we like to think about applications, and there are many. One fun application, which really does get used in animation studios, is something called Harmonic Coordinates. This is a tech report from Pixar that I just grabbed preparing these slides. So the basic point here is I designed these harmonic functions to be 1 at one control point and 0 at all the other of a deforming shape. And then what I do is I have, this thing is some cage around a deforming animated character, and I move the control points and I want to know where the rest of the character went, right? And what I do is I take the displacement of the control points and I just average it to the points in the interior of this thing using the weights that I got from solving a harmonic problem. And this is actually a pretty reasonable way to do deformation. And you can see here, I think it was used in the Incredibles. Yeah. By the way, this is also using one additional kind of cool property of harmonic functions, which is that you can kind of construct a partition of unity in a sneaky way. So if you have a 1 and then a 0 on all the other points, and that's sort of your boundary condition in this expression here, and then you construct one of these for each of these control points, you can double check that the sum over all of the functions that you get when you construct that set is always equal to 1. Is really what's hiding here. Okay, so this is all to say that already we have some nice application. And notice that essentially the only thing that this application cares about is smoothness, right? It's just saying that, well, I kind of want the effect of this control point to just die off as I approach the other control points. And there are many extensions of this work. I mean, this is sort of cottage industry and computer graphics academia is to come up with nice bases, and most of them begin with like, I want to minimize Durational energy, but now I'm going to throw in some more constraints, and that's make it biharmonic, or you can make it, I don't know, I think there's even a triharmonic one out there, where I take the Laplacian and I cube it because I want it to be really smooth, and so on. Okay, so for our purposes, since we're talking about spectral problems, of course, once again, we can double check this sort of positivity and self-adjointness property. So in particular, let's make our space of functions, again, be the set of functions that are just 0 on the boundary because your instructor is lazy. Then, right, well, what happens if I take the inner product of f in itself? Well, in some sense, I can undo the expression on the upper left board here, right? I can unintegrate by parts. Yeah, I kind of read it in the vertical direction, and what do I get? I get the Durational energy, right, which is the integral of the norm squared, so it's a positive number. Yeah, and so our operator is positive semi-definite. Yeah, and similarly, in essence, what I applied here was self-adjointness, right, or like kind of the symmetry of this delta operator. Yeah. So once again, what do we have? We have a thing that inputs functions, outputs other functions, acts like a second derivative, has nice eigenfunctions which kind of correspond to the vibration modes of a drum. And indeed, okay, so far we've talked about where the Laplacian comes up, but we haven't really talked about the can you hear the shape of a drum style problem. And I thought for one additional way to motivate this thing, we could motivate Laplacian eigenfunctions one more time using sort of a slightly more kind of interpolation style thing. Right, so let's say that I have a region omega. Oh, this is going to be the board that screws up. And I just want to find a smooth function on omega. Yeah, just because in some sense, I mean, think about the Fourier basis, like cosines and sines, right? It starts out with really smooth stuff, like constant function, right? And then you get slightly less smooth thing, like 1 sine wave, and then a slightly less smooth thing, 2 sine waves, whatever. Yeah, I could try and find a similar sequence on a generic domain omega with Dirichlet boundary condition by doing something like the following. So, right. So, what is the smoothest possible function, at least with respect to Dirichlet energy on I don't know a region omega here in the plane? What was that? 0. Can you name a second function that's also smooth? 3. Yeah. Any constant function is equally smooth here. Yeah. So we somehow have to kill that to do anything interesting. Yeah. So one way to kill that, notice this is the same thing as kind of like minimizing the norm of x without any constraint on x. Yeah. So one way to do something more interesting is to put a constraint on the norm. Yeah. So in particular, I could look for critical points of the Dirichlet energy on this sort of unit sphere of functions, I use sphere extremely loosely here, to be the set of functions u, so that when I integrate u squared in my domain, I get 1. This is some notion of sphere. Right? It's all the things that are unit length with respect to this crazy dot product we've cooked up. Yeah? So first of all, remember one funny way to motivate eigenvalues is like I have this map, right, that goes, right? This is some function which goes from vectors to scalars, right? X transpose AX here. Let's say A is semi-definite for a second. Then what is the minimizer of this thing? 0, yeah? So to kill that, once again, we sort of add this constraint, right? And what are the critical points of X transpose AX subject to the norm of X equal to 1? Well, it's exactly the eigenvectors of A, right? I think we showed that in the second lecture. So we can do exactly kind of an analogous thing for functions on omega and ask the question of, well, what are critical points of the durational energy subject to the constraint that functions square integrate to 1? Yeah? So how do we do constraint optimization? Well, we use Lagrange multipliers. Conveniently, how many constraints do we have? We just have one, right? This isn't like one of these crazy infinite dimensional things. In terms of constraints, it's just infinite dimensional in terms of use. Yeah? When we do optimal transport, or when Sebastian does optimal transport, because I'll be out of town that day, you'll have to cope with infinite numbers of constraints, and then you're in a very different regime. But for now, one thing we can do is say, okay, so let's make a Lagrange multiplier. So what is this going to do? It's going to take in a function. In addition, it's going to take a Lagrange multiplier, and this thing is just a real number. It's not a function. Yeah? So u is a function, and the Lagrange multiplier is a number. Right? And remember what the Lagrangian is? You take your objective function, and you add to that lambda times the constraint. Yeah? So here we'll get 1/2 the integral mod gradient of u squared dA. And then to agree with the course notes, well, what do I want? I want it to square integrate to 1, so I can do that like that. Yeah. By the way, do you see that it's fair to put a 1/2 here? This is essentially like saying 1/2 of the square integral is equal to 1/2. Okay. So do you guys get that this is the Lagrangian? Fabulous. So once again, what do? Well, we just take the first variation and we set it equal to 0. It's the only thing we know how to do. Yeah? And what happens when we do this? Well, it's using exactly the same argument here, right? I get, 0 equals d over dh of lambda with respect to u plus hv. And for now, let's take v to be a generic variation, and then we'll come back and add boundary condition in a second. Right, because remember how you deal with Lagrange multipliers? You take the gradient with respect to u and set it equal to 0, and you take the gradient with respect to lambda and set it equal to 0. They're both true. Right, so essentially we can follow the same calculation as before. Yeah? And conveniently, well, what do we get? Well, the first thing, the first term is just the same gradient we already computed. And now we just have to deal with this least squares thing, but this isn't so bad, right? Because the gradient of u squared is just u, yeah? So at the end of the day, what do we get? Well, we get the following expression, which is missing a term in the course notes. So somebody please remind me about that, which is the integral over omega of, let's see, v times, right? So this is the same as the argument we have here. Yeah? But now we have to cope with this term here, right? So we get minus lambda u, right? And then if we want to be careful about dA, our boundary condition, so I'm making no assumptions on u or v, then I need an additional term, which is the one that I sliced out over there, right? So this is v times the gradient of u dot product with the normal. Okay. So take a look at what's happened here. What's hiding inside of here? This is an eigenvalue problem, yeah? So that's the kind of nice thing is when we talk about this, can you hear the shape of a drum problem, a different way to view it is really, Laplacian eigenvalues, you can think of it as like progressively smoother, or I guess progressively less smooth functions, starting with the constant one. right? Because the energies are exactly the lambdas here. Okay. Right. So we now need to bifurcate a tiny, tiny bit and talk about boundary conditions. So this first variation formula I took is completely generic. I haven't made any boundary assumptions on U or V. Okay? And the reason for that is there's actually two different eigenvalue problems that are hiding here. Right? One of them is the Dirichlet eigenvalue problem, one's the Neumann eigenvalue problem. Okay. Oh, incidentally, I slipped something past you that I really should have checked. Remember that our objective function, right, looks like u times Laplacian u after integrating by parts, right? And I just showed that u is an eigenfunction, right? So this is really lambda times the integral of u squared. This is just lambda, right? So in other words, the eigenvalue really is measuring some notion of smoothness, right? Dirichlet energy here. Okay, right. So. The basic two boundary conditions that we're going to consider are to put some additional assumption on our function u. The first one would be maybe I look at critical points of Dirichlet energy subject to just a constraint that u on the boundary is just 0. Yeah? Notice that u has to square integrate to 1. So even though u is 0 on the boundary, like something interesting still happens in between. Okay, so this is known as Dirichlet boundary condition. Okay, and what happens in this case? So in this case, well, what do we know to preserve that when we take our first variation? We know that v had better equal 0 on the boundary, yeah? Because we got it when we vary u, we can't violate our boundary condition. So in particular, we just get for free that Laplace u equals lambda u in the interior of omega, and that u on the boundary is just 0. Right? That's what you can kind of read off of here, right? Because this is true for all v subject to the 0 boundary condition, so that second term just goes away. Okay. But what if I don't want to make that assumption? Right? I mean, I've been doing it because I'm a sloppy mathematician, but like, what if I just want the sequence of all the smoothest functions in omega, right? There's still an interesting sequence, and there's no reason why that thing really should be constrained to be 0 on the boundary, right? That's like a constraint I made up for sloppy math. Yeah? And so I could ask exactly the same question otherwise. Well, in that case, what do I know? Well, for one thing, remember, this is still true for, now it's true for all v, not just v that vanish on the boundary. Yeah? Because if I take v that's non-zero on the boundary, that's fine, because I'm not making any boundary constraint condition. Do you see that? So let's think about two different cases, right? One is that my variation v just has interesting values and some patch in the interior of omega, right? So in other words, the second term still vanishes for all of those functions v. Yeah? So in particular, so here we're going to have no assumption. You can say, well, this is still true for all v, including the v that vanish on the boundary. So in particular, we have that Laplacian of u is equal to 0 in the interior. But we have an additional thing that we can learn, which is now I'm going to cook up a sequence of v's which just barely touch the boundary and move closer and closer and closer and closer and closer to just touching a boundary point. Okay? So now what happens to the first term in this pair of terms? Well, this is an integral over the region, right? I'm touching less and less of the region, so what happens to it? It vanishes. Yeah, that's absolutely right. And then what's left is this thing, which is a boundary integral. Right? This is true for any choice of crazy v's on the boundary. So what must be true? Yeah, the gradient of u dot product with the normal is equal to 0 on the boundary of my domain. Notice that kind of a magical thing happened, which is like I said, okay, I'm not going to be a sloppy mathematician. I'm going to remove my boundary condition and actually just work out this expression. And then what happened anyway? I got a boundary condition. Right? This is kind of surprising. Is anybody, so I can actually say something qualitatively about these eigenfunctions u, right? Oops, it's not, that's you should have caught me. Yeah, like that, right? Oh boy. Oh no. Yeah, that's right. Okay. But that somehow qualitatively a special thing happens that when I compute the eigenfunctions, they have the special property that when I take their gradient, I dot product it with the normal, I get 0. Anybody know what this boundary condition is called? Yeah. It's called Neumann if you're a physicist. What would be called if you're a mathematician, given the derivation we just made? Natural boundary condition. And they're natural in the sense that I started with no boundary condition, and it was just a byproduct of the way I took my derivative. Yeah. And so the point here is that even if you don't intend to enforce a boundary condition, often one comes out just because you integrated by parts, and that's life in the city. Yeah. So that's the basic message here. There are a few common misconceptions we should note. One, so a really beautiful property of harmonic functions is that they are twice as differentiable as their right-hand side. So like if I have the slightly more general version of Laplace equation, like Laplace of u equals some function f of x, then the thing that I get out of solving that partial differential equation is 2 times more differentiable than what I started with. This is something called elliptic regularity. But that property is not true at the boundary points. It's only true in the interior of my domain. And roughly, the physical system you should have in mind is some kind of tent pole, right? So the tent here is a very smooth function. But if I add like point constraints, like in my learning problem I described to you guys, take a look at what happens at these points. They become singular, right? So I have a differentiable function everywhere except right at the points where I actually know something about my function. This is actually a big drawback of that harmonic weights interpolation algorithm I told you before, which is if I pull on the hand of my animated character, if the hand is too close to the control point, what do you think happens? Well, the finger pulls out way more than the rest of the body because somehow that effect decays very quickly around that control point. There are easy ways to fix that. One is to use the second derivative instead of the first in Durational Energy, which gives you a different thing. Yeah, so this is just the key phrase to remember for this. If you're at a bar and you want to do some bar trivia, this is called loss of ellipticity. The reason being that, well, ellipticity, like this nice differentiability property, is lost right at these key points. Okay, so maybe really quickly, I think we can do the case of graphs, and then we'll save manifolds for next time, which is good because I did some sloppy math this morning and I was nervous to do it in class today. Okay, so. Now we're going to kind of take a step to the side and talk about a very different object and then see that the same story still applies. Okay? So now I have a graph. Graph has a bunch of vertices and edges. And I'm going to think about a function on a graph as an assignment of one value to every vertex. Right? So maybe I have, the social network, and every node is labeled with, I don't know, the income, and Mark Zuckerberg wants to know whether or not he should try to extract money from you or not. Yeah? And so, maybe I'm giving some labels on some nodes, I don't know labels on others, I'm trying to impute them in a way that sort of makes use of the assumption that I'm only friends with people with similar level of income to me, which apparently is remarkably true in social networks, which is too bad. Yeah? Okay. So here's a question. So if a function is assignment of one value per vertex of a graph, what is the durational energy? What is some reasonable way to measure its smoothness? Any ideas? Don't all speak at once. Yeah.
Well, it might be like probably the change from between a vertex and all of its neighbors, because that's sort of like the second derivative of a graph.
Yeah, in fact, you kind of jumped over a step. So Colton's absolutely right. So I have an assignment of one number per vertex of a graph. So some reasonable replacement for gradient might be on every edge to take the value at the 2 endpoints and just subtract the 2. Right? So durational energy would be what? Just taking all those numbers and squaring them and summing them up. Yeah? In fact, if you go back and you look at the Laplacian that we did in one dimension for that spring, you'll see that's exactly what's going on. That's one way to prove that it's a positive definite matrix. Okay, right, so let's formalize that a tiny bit. So I'm going to make a matrix D. Now we're really in matrix land, so we don't have to worry about all this sloppy integration by parts business. And D is edges by vertices. Okay, so it's not a square matrix. And D, I'm going to take every edge and just arbitrarily orient it. I'm going to flip a coin and just stick an arrow on it. It's not going to matter what direction. Okay, and I'm going to find D to be the matrix which is -1 at the tail of every arrow and +1 at the head of every arrow. So there's a row in my matrix for every edge of the graph, right? And essentially what this does, it takes one number per vertex, and it gives you a list of all the numbers that are per edge of the difference on the two endpoints. Does that make sense? Okay. Great, so in some sense, the map from some function per vertex to D times that function is kind of like a gradient, right? This is some notion of rate of change. Yeah? So if I want durational energy, what could I do? Well, that's one number per edge. It's still some vector. I can just take its norm, right? And that is exactly durational energy of a function of a graph. So I take D of that thing, and I just take its two norm. This is much simpler than what we had before. Of course, remember and here's an alternative expression, right? So I just iterate over every edge, I subtract the values on the two endpoints, and I square and sum. Yeah? So what's the great thing about a norm? The norm of a vector is just dot product of the vector in itself. Yeah? So of course, norm of df is equal to f transpose d transpose df, right? This is dot product with itself. And now I can parenthesize this thing. Notice this is a positive definite matrix. In fact, here I've exposed it, right? It's D transpose times D. What do you think this matrix, what do you think we're going to call this thing? This is the graph Laplacian. Yeah? And indeed, the graph Laplacian has a lot of really beautiful structure. For one thing, just like Colton actually suggested, he kind of predicted 2 steps ahead of time. This thing has a 1 for every neighboring pair of vertices and minus the degree down the diagonal. Right? So in essence, what is this thing doing? It's taking the value at a vertex and subtracting off the average of its neighbors. Right? In this case, kind of scaled by degree, but whatever. Yeah? It's a positive definite matrix, kind of just by construction. Yeah? And it looks an awful lot like sort of a spectral object. Yeah? And then remember, actually, as a special case of this matrix, includes that one-dimensional thing that we constructed at the beginning of class. Yeah? So there's a nice connection. So there's all kinds of beautiful things we can say. One is, first of all, what is the smallest eigenvalue of this matrix? 0, right? I mean, if I put a constant value on every vertex, I get 0. Yeah? But does anybody know the name of the second smallest eigenvalue? The corresponding eigenvector? This is called the Fiedler vector of my graph. It has lots of really beautiful properties. So here's an example of a Fiedler vector. Notice that it kind of goes from small to big. It contains no local optima. That's not a mistake. Of course, it's a little bit suggestive the way I've drawn this picture, because do graphs really have a boundary? No, right? It's not clear what's a boundary and what's inside. It's only because I drew it like a dumbbell here. Yeah? But in any event, this thing is a Fiedler vector, algebraic connectivity. A very easy way to do graph partitioning is to take this object and cut it along edges where the sign differs on the two sides, right? That'll take this object and cut it in half in a very nice geometric way. And what we'll see is when we talk about Constraint Theorem, there's nice geometric intuition for that. Or if you're taking a graph theory class, you've probably seen it in graph partitioning. Remember, we also talked about the mean value property, right? That if I take, for harmonic functions, if I take an integral over a little ball, I get the value at the center. We'll take a look. If I have discrete harmonic functions, right, like Lx equals 0, well, then that's kind of true by construction, right? That every vertex is equal to the average of its neighbors. Yeah? Much easier to do stuff in discrete case, right? I like discrete math. Yeah? So indeed, the graph Laplacian, there was this big effort probably 20, 30 years ago that essentially took all these things, these beautiful theorems we know about the smooth Laplace operator, and asked this question of how many of them can I carry over to graphs. In fact, it's not even just 20, 30 years ago. It goes all the way back to Kirchhoff, whatever, the circuits guy. And indeed, one of the neat things is, first of all, almost all of the story we'll tell in this class, you could write in terms of a graph and it would make perfect sense. Thing one. Thing two is that actually the graph Laplacian encodes all kinds of cool combinatorial structure that's just independent of the smooth geometry we'll talk about. So a great example of this, so let's say, all of the eigenvalues of L here include 0. But what if I looked at all the non-zero eigenvalues of L? And I can do something kind of crazy that I couldn't do in the smooth case. So eigenvalues in the smooth case go off to infinity, right? I can't multiply them together. But here it makes perfect sense, right? So I can take some notion of the determinant of L after kind of getting rid of the 0 eigenvalue, just by multiplying them all together. Does anybody know what this gives you? The determinant of L? Only recently, by the way, in modern geometry, they managed to link this to smooth Laplace operators, involves like weird zeta functions and stuff. Now, this has been known all the way to the 1800s. The determinant of L is actually the number of spanning trees after you divide by the number of vertices. This is like a purely combinatorial result about graphs, but it's hiding inside of spectral stuff. Yeah? And so there's this really beautiful textbook which essentially tries to take the PDE language we'll develop in class here and just do all of it in graph theory, but then in parallel with that, show all the cool combinatorial things that you can read off of a graph and sort of interpret them in terms of derivatives and so on. So we'll conclude today by a quick survey. What do you think? Can we hear the shape of a graph? I mean, we can hear the shape of an interval. Somehow we're not that far off. We just glued them all together. What do you think? Yes? No? I'm totally not going to raise my hand. I don't care what you ask. Yeah, that's what I thought. Yeah, so the answer is no. So here's an example. I think this is the minimal example of two isospectral graphs. These are called enneahedra. And indeed, what these contain 1, 2, 3, 4, 5, 6, 7, 8 vertices. And if you just construct that matrix, which I encourage you to do, go home and just do it in MATLAB. It's not that hard. Compute the eigenvalues. You'll see that they're the same. The eigenvectors, however, are not the same, which is going to lead us to some of our kernel signature stuff we'll talk about later. Yeah? So unfortunately for us, in this case, like, you could almost hope that like you could hear the shape of something because you really can get the complete list of eigenvalues here, but the answer is no. I like that you're like pointing your finger. Can you compute the eigenvalue in your head? I'd be very impressed. Enneahedra? Oh, I don't know. I've always thought of this as the definition. I suppose it does have something. There's some polyhedron sitting underneath this. Yeah, I don't know. Yeah, this is some connectivity graph. I think probably, I don't know. At least one of them is. But I'll let you figure that out. Okay, so we'll call it for today. Next time, hopefully you've gotten the point, which is, what is a Laplace operator? Well, it's a lot of things. It's a thing that compares a value at a point to the value at its neighbors. It's a thing that measures the smoothness of a function. It's a thing that comes from the wave equation. It's a thing whose frequencies tell you something about geometry, and you can sort them kind of by multiple scales. And so the only thing that we're missing is what to do when we have curvature, because now this nice formula where you have the sum of second derivative doesn't make any sense, right? We don't know how to take second derivatives of functions on surfaces. Yeah, so that's where we'll maybe stop today, and next time we'll consider this sort of case of functions that paint colors on a bunny. And I think we have all the material we need to define it in not too painful of a fashion. And then we'll be done. We'll discretize it. We'll compute eigen stuff. We'll do all kinds of cool shape matching applications, all that good stuff. Yeah. So with that, I will see you guys Thursday, I guess. And yeah, don't forget your reading assignment.